Greetings, dear ladies and gentlemen. I welcome you all to TV Markup. My name is TV, and here is my contact in case you need to get to me. And you can as well send me an email via this email address. Once again, I'm glad to have you all here for another important lesson in our A-Level vector series for paper 1. Vectors is one of the compulsory topics in A-Level mathematics as per the guidelines from NCDC. So this will be in the part that is called geometry, and that is section B. So this is one of the compulsory topics for section B. So it is very important that you give it your full attention because it contributes heavily to examinations, and it is one of the topics you cannot afford to ignore. So far, in lessons 1, 2, and 3, we have moved step by step from the introduction to vectors in 3 dimensions, equations of lines, collinearity of points, and we have as well looked at several standard UNEP applications on lines. In our previous lesson, we talked about how to show that a given point lies on a line. We looked at what we call some of the examples, and as well we talked about the shortest distance. We talked about the shortest distance from a point to the line. We as well discussed about that. So we basically looked at one method of finding that shortest distance, and this is the method that we looked at. So in our today's lesson, that is our lesson number 4, we are going to continue with the shortest distance from a point to the line. Now for this case, we shall focus on using the formula method to solve such questions quickly and accurately. So as we continue, we shall also move deeper into vectors, and later we also cover planes, so that by the end of this series, you will have a complete understanding of the vectors topic through a TV Math. Please don't miss any lesson. Don't miss any lesson, because every lesson builds on the previous one. And apart from vectors, remember we also have some of the series that are ongoing. So if you come to TV Math, go to the playlist, we have some of the series that are ongoing. For example, we have ongoing A-Level, a new curriculum, revision items. So that one is here, A-Level, new curriculum, revision items. So when you come to this playlist here, you'll be able to find a lot of the questions that we have so far discussed about. So please come and check some of these questions here to guide you on what is basically expected from the responses. So here is our item number 3 that was done. Please check for such items. They are very important to guide you on how your standard A-Level questions will be appearing. So here are some of the other items. So I also uploaded the standard A-Level paper 2 according to the assessment objectives. It is also there. So check that video as well. Item number 2 was discussed. It is also there. So please check for all these items at TV Math. So as you are trying some of these items, please don't forget to subscribe to TV Math. Don't forget to like and share our videos. So apart from the ongoing A-Level new curriculum revision items, we have also got another series that is ongoing. So that one is about trigonometry. That is also about trigonometry. And as well, you should be aware that also trigonometry, like the way we said for vectors, is also among the topics that will be in that section that is compulsory. So we are handling all the compulsory sections here at TV Math. So that section there is very important because you will not miss to do a question there. So since it is compulsory, it is also important that we give it much attention. So we have ongoing lessons on trigonometry, and here is the playlist. So when you come to that playlist there, you'll be able to get the lessons that we have so far uploaded, starting from the scratch. Remember, all these started from the word go, from the introduction, from the scratch. So check out our videos and make sure you follow along. Don't be left behind. And of course, don't forget to share such videos with your classmates. It is very important. Now, here we have so far uploaded 2 lessons. That is lesson 1 and lesson 2. And other lessons are also being uploaded, and soon we shall have all other complete lessons for trigonometry and vectors. So please make sure you follow along. So this was our lesson number 2. This was our lesson number 2. Please go and check out that video. This was our lesson number 1, which was about the introduction. So please check out all these videos. So we have a lot at TV Math Hub that is ongoing. So for you not to miss all these, you need to simply hit subscribe. Don't forget to like and share this video. Turn on your notification. Turn on your notification bell so you can always get notified. So this is where we began trigonometry from the word trigonometry, understanding whatever is needed for you to know about trigonometry. So please go through some of these lessons that we are uploading. So at TV Math Hub, we have as well discussed several standard examination questions already. Many are uploaded, so simply go to TV Math Hub, search for whatever you are looking for. So make sure you check out all these videos right here at TV Math Hub. And if you are new to this channel, please subscribe, turn on the notification bell, and share these lessons with your fellow students. Now, without wasting time, let us begin our today's lesson. So today we shall be talking about the formula for the shortest distance of a point from a line. So let us look at how best we can derive that. So we want to look at the derivation of that formula. We want to look at the derivation. So how do we derive that formula? I want us to consider a line with a vector equation. So we want to say that suppose a line has a vector equation which is given by vector r, which is equal to a plus lambda vector b, where this vector a is the position vector of the given point, the position vector of the given point a, which is on the line, and the b is the vector parallel to the line. Now suppose we have a vector equation r, which is equal to vector a plus lambda vector b. Of course, a is a point on the line, and vector b is what we call the vector that is parallel to the line. So here is what we are talking about. So we have our plane. So this is our x, this is our y, our z, and this is our y. So suppose we have a line here. So suppose we have this line. So this is our line. So on this line here, we have also got a vector that is parallel to that line. So let's put that vector that is parallel to that line. So we are considering a point A on this line. Then I want us to consider another point P. This is the point that we need as our reference point. So that is the point where we need to get the distance from that given point to this line. So where the line, the perpendicular line segment from this point meets this line here, this is our line. So where it meets this line, we want to call that point to be a point like T. So that is our point T. Now, I want us to make this angle, this line here that comes from P, to be making an angle to be making an angle theta with respect to this line here. So if we put this line from point A to join with point P, now I want this one here, this line that is joining A and P, to be making an angle theta with our line. So for the other case, we were simply looking at this distance from P to T. That was our particular interest. But now we are including another line from P joining a point on the line which is point A. Now that is what we want to look at. So if you have this, so we are looking at P as our reference point, and as we can see that AP makes an angle theta with the line, and that the perpendicular from P meets the line at the point T. So all other things will remain the same. So we can simply describe what we have put there. We are saying that let us suppose also P is a point. So let us say, or suppose also P is a point, of reference, and that vector AP makes an angle theta with the line, and that also the perpendicular, from our point P to the line, meets the line at point T. Also, we have got vector B as the vector which is parallel to the line. At the same time, we can easily see that the required distance that we are interested in is D, which is same as magnitude of PT. This is what we are talking about. We are simply describing what we have drawn here. So we are having our point P. This is our reference point. This is a point for which we need the distance of the perpendicular line segment from this point P to the line. But we are saying that if the line from point P meets this line here at a given point T, so we are rating this to be point T. And then we also want to have the vector P to A to be making an angle theta with this line here. So of course this B is the vector that is parallel to this line, and the required distance is D, which is this distance. PT is the distance or the length PT. So that is basically what we have described there. Now, from this, since this is a perpendicular from that given point, then this is a right angle triangle. So when I consider that triangle there, what will be sine of theta? From this triangle, what will be sine of theta? Sine of theta will be opposite, which is D, divided by this length here. AP, divided by the length AP. So in other words, sine theta is same as the length PT divided by the length of the vector AP. Isn't it? Opposite over hypotenuse. So that is what I want to talk about. So I want to look at that. I say that from the figure above, we can easily say that sine of theta is same as magnitude of PT, that is vector PT, divided by magnitude of a vector. It was what? Vector A to P. Vector A to P divided by magnitude of vector A to P. So from here, can we therefore say this is same as magnitude of PT is same as magnitude of AP sine of theta when we cross multiply. Now, I want us to refer from the definition of cross product. From the definition of cross product, what will be vector AP across vector B? This is same as having magnitude of AP times magnitude of vector B sine of theta, isn't it?
Yes.
By definition of cross product, we can write this. But since I'm interested in length, I want to have this as magnitude as well. So magnitude of AP times that one to be equaling to that. Such that at this given point, I can have AP. I want to make vector AP sine theta the subject, the way it is here. When from here, when you make vector AP sine of theta the subject, what remains? You will have magnitude of vector AP cross vector B divided by magnitude of vector B. Is it? When I divide by magnitude of vector B on both sides, I will get this, isn't it?
Yes.
So I will have this equation. I will also have this equation. So from these two equations, what should we conclude? From these two equations, can we say from equations 1 and 2, can we conclude that AP here, sin theta is PT. So can I say that magnitude of PT is the same as magnitude of AP cross vector B divided by magnitude of vector B?
Yes.
From this, when I make this one here the subject, I will have it as vector PT. So when I substitute for AP sin theta, this AP sin theta is substituted with this. I will be able to remain with this.
Yes.
So this one here is the magnitude of PT. So when you look at this, our interest is to get magnitude of PT, which is D. So in other words, magnitude of PT is same as AP. That is A to P. This A to P. Then you cross it with vector B. Then you divide by the magnitude of vector B. So that is how we obtain that. So in other words, in case you have AP, because we know AP is same as OP minus OA, because all these two points will be given. Vector, the point P will be given, point A will be given, the direction vector, you will be knowing it. So you simply substitute in this expression. So AP is same as that, is same as vector P minus vector A. So it implies that when you are looking at the distance, the required distance, vector PT is the same as getting magnitude of P minus A cross vector B out of magnitude of vector B. So that is the required distance. So the required distance will be obtained. The required distance will be D, which is same as magnitude of PT, which is actually same as magnitude of vector P minus A cross vector B divided by magnitude of vector B. So this is by the formula of how we can obtain what we call the shortest distance of a point from the given line. So from this, what is the most important thing is, if you are given the point P, then you also have the point A, that is a point on the line. Simply get A to P, get vector AP, then cross it with the parallel vector, divide, then take the magnitude, divide it by the magnitude of the parallel vector. So that is by the formula. If you want to get it from the first principles like the way we did, then you follow this one here, these procedures here. So we shall also look at some examples on how we can also use or apply this formula here. So let us look at some of the examples as well. So you will choose the method which is easier for you, and that is the one you will apply when they ask for the shortest distance from a given point. So we can look at this example. Find the shortest distance. Find the shortest distance of a point P. P is given as 1, 1, and 5 from the line whose equation is r, which is equal to 2 plus lambda into I plus 1 plus 2 lambda into j plus 3 plus 4 lambda into vector k. So that is what we need. Now, you must recall the expression, but even if you don't, what you do, you can do some simple sketch. So you are given a point P. This is the point, which is 1, 1, 5. You need the perpendicular distance from this point to this point here. That is a point on the line. This is your line. So this point on the line, you can let it to be P. But on this line here, you have also got another point. You have also got another point, which is point A. So on this line, you also have another point. That is point A. That is a point on the line. So you join this with that. When you join it with that, of course, this is at a given angle theta. But what is our interest? Our interest is to get A and to get this parallel vector B. So what is the parallel vector D? Parallel vector B. Then what is point A? Point A is a point on the line. This is the parallel vector. So from this line, let us look at that. From this line here, what will be the equation of the line? So the given equation is, so what will that equation be? Let us look at this equation. How can we simplify it? This is vector R, which is, what is that point? 2, 1, and 3. 2, 1, and 3 plus lambda into, what is the coefficient of lambda here? Is 1, is 2, is 4. So we can easily get it like that.
Yes.
I hope this one is okay.
Yes.
So the values which are not having lambda, they will form this point. The ones which are coefficients of lambda, then put it here as your direction vector. So for that case, what will be B?
B is 1, 2, 4.
B is 1, 2, 4. What will be A? A is a point on the line.
Is 2, 1, 3.
Is 2, 1, 3. So this is the point on the line. This is the direction vector, which is the B. So the given equation of the line is R, which is 2, 1, 3 plus lambda into 1, 2, and 4. Now from that we are able to get A, that is this one here. So we are able to get point A. We are able to get the vector for B, and we also have this one here. Recall that our distance is the same as magnitude of A to P, crossing it with the vector B, divided by magnitude of vector what?
B.
Vector B. So what is your interest? Your interest is to get point A. Your interest is to get point P, which is there. Your interest is to get point B, which is here. So with that, it means our vector A, when we compare this with the equation of the line, we should be able to say that I can maybe put it here by comparison with the general equation, with the general vector equation, which is R equaling to vector A plus lambda vector B. So we can say our vector A is 2, 1, 3. Our vector B is 1, 2, and 4. So by a definition of the formula for getting the distance, then we should be able to have from distance which is equal to magnitude of A to P cross vector B divided by magnitude of vector B. What do we need first? We need to get AP. We need to get A to P. So we have our A, we have our P. So we can maybe put it here. Our A is 2, 1, 3. Our P is the point which is given 1, 1, 5. This is 1, 1, 5. And our vector B, we already have that. Now, let us first get AP. So AP is same as OP minus OA. So OP is 1, 1, 5. OA is 2, 1, 3. So get this as negative 1, 0, and 2. That is what we shall have. That is AP. But we also need AP. We also need AP cross vector B. So let us get that AP cross vector B. So here we have I, J, and K.
Okay.
So our AP is negative 1, 0, and 2. Our vector B is 1, 2, 4. 1, 2, 4. So this will be equal to, I think we can do this at once. You still recall what we do.
Yes.
Eliminate this and this. Get the determinant of this remaining one. So can we do that at once? What is that determinant? 0
Negative
times 4
0.
minus 0 times 4, 0. So that is 0 minus
Negative 4.
0 minus 4
4.
into I.
Mm.
We subtract it. Next, we shall get this one out and this one out. We remain with this and this, which will give us negative 4, this and this, minus 2 into J plus. Next, we shall remove this one and this, and that will give us negative 2 minus 0 into K. So this will be same as having negative 4
Negative
I
minus negative 6J.
minus, that will be plus
Yes.
6J. Then minus 2 vector K. That will be our AP cross our AP cross this one here. But remember, we also need to take its magnitude. So let's take the magnitude of that. So magnitude of vector AP cross vector B. What will it be equal to? Magnitude of that will be negative 4 squared plus 6 squared plus negative 2 squared. And this will give us 16, 36, 52. Is it 56?
Yes.
56. So next we need magnitude of vector B itself alone. So what will be magnitude of vector B? Vector B is 1, 2, 4. So that is 1 squared plus 2 squared plus 4 squared, which will give us magnitude of
21.
this is 5,
21.
21. So now, so for D, which is magnitude of AP across vector B divided by magnitude of vector B, we shall have this as the square root of 56 over square root of 21. So you can combine these under the same square root, 56 over 21, since they are all under square root. Let us put by what? Which one enters? 7. 56 divided by 7 is 8. So this is same as square root of 8 divided by 3. So Can we simplify this? This will be
0.356
0.3563 units. So that will be the distance D, and that will be the required distance. So for the formula, that is what we do. What you need is to get AP, cross it with vector B, then get the magnitude of that divided by the magnitude of vector B. Because here, from the line, get the A, get the this parallel vector. This point P will be given, and now from there, get D from this given expression. So that is how you obtain the distance from the distance of a point from a given line. So you will try for me this question as well. So here you use any of the methods, but it's better to use all the methods so you can get used to the two methods. So for each of the questions, use the two methods and see if you will be getting the same answer. So the question one will be find the perpendicular distance from the point A, which is 4, -3, and 10, to the line with vector equation, which is R 1, 2, 3 plus lambda 3, -1 and 2. We'll try out that. The next question is saying that find the equation of the line through the point So find the equation of the line through point Q, which is 2, -1, 4, and perpendicular to the line with vector equation I plus 2k plus lambda into 2I plus j plus 2k. So next, we are saying find also so that is the equation we are having there. So I want us to first look at this one together. For this one, you will try it. I want us to look at this question here together here. So they are saying find the equation of the line through this point and perpendicular to the line with this vector equation. And find also the distance of Q from the line given. So that is what we need to look at. So For that one there, let us first try to draw a simple diagram, because it becomes easier when we try to sketch this one here. So we want the equation of the line through the point Q. This point Q is a point which is 2, -1, and 4. But it is a point. We want the equation of the line through this and is perpendicular to this line here. So this is our line. So this is perpendicular to that. So it makes 90 degrees with that. Let us call this point as point B. This line, of course, has got what we call the parallel vector B, which is that. Now, from the given line, our line is R, which will be equal to, what will that one be in vector form? In vector form, it will be equal to
2, 1, 2.
1, 2?
2, 1, 2.
Are you sure? This is I plus 2K.
These are 102.
That is 102 plus lambda into
212.
212. That is our line there. Now, so we are letting the perpendicular. So we are letting, or we have let the perpendicular. Let the perpendicular from Q meet the line at a point T. Let the perpendicular from Q meet the line at point T. And then that implies that vector T satisfies the equation of this line. Satisfies the equation of that line. That is our line. So it satisfies 102 plus lambda 2212. We are following the similar procedures as we did when we were looking at the distance from a point to the line. So this is same as having 1 plus 2 lambda. This is lambda. This is 2 plus 2 lambda. So next, we are told that QT is perpendicular to the line. Is perpendicular to the line. So if it is perpendicular to the line, then it is also perpendicular to, what is it perpendicular to? Is also perpendicular to, if the line from Q is perpendicular to this line, what else is it perpendicular to?
Vector B.
Vector B. So it is also perpendicular to B, which implies that when I get QT, I dot it with vector B, I will get what?
0.
I will get a 0. That is what we have. Now, what is QT? But Q to T is same as, Q to T is same as OT minus OQ. So OT is this. This is the OT. This one. So this is same as having 1 plus 2 lambda, lambda 2 plus 2 lambda. This we subtract OQ. OQ is that given point 2, -1, 4. 2, -1, and 4. So this will give us -1 plus 2 lambda, 1 plus lambda. This is what?
6.
This
2.
is -2.
Yeah, -2 plus
2 lambda.
lambda.
But we know that QT, so from this, we know that -1 plus 2 lambda, 1 plus lambda, -2 plus 2 lambda, dot vector B B is the parallel vector. Parallel vector is which one? What is vector P?
2, and 2.
2, 1, 2. Okay. So this is dot 2, 1, 2. We shall get a 0. So let's multiply that. Negative 2 plus 4 lambda plus 1 plus lambda minus 4 plus 4 lambda will be equal to 0. 4, that is 9 lambda, which is plus negative 2, negative 1, negative 5.
Yeah.
So lambda is same as 5 over lambda. 5 over 9. Okay. So we have obtained the value of lambda, which is 5 over 9. Now, remember that we need the equation of the line through this point, which is perpendicular to this line. So if it is perpendicular, how shall we get the equation of that line? First of all, we must know A, we must know lambda vector B of this line here. So I can use B prime. So we can easily see that this, when we look at this line here, the line that is passing through Q and is perpendicular to this line here. This line, we need its parallel vector. Okay? Because for A, that is a point on the line, at least we have that, which is this. And then B prime is what we are looking for first, because we don't know that. But of course, we know that this line here is parallel to Q2, QT. So the parallel vector that we shall consider will be this vector QT, because this line which is passing through Q is parallel to the vector Q to T. Is that one okay?
Yes.
Yes. So at the first we are looking for the equation of the line through this point, and that line is perpendicular to the line with the vector equation this. So this is the line which is passing through the point Q and is perpendicular to this line, and we are saying this one is meeting this one at point T. So that is what we are looking for. So in other words, we are basically interested in getting QT. So this QT will act as the parallel vector that we shall put here. This A will be the Q. So that's why we are looking for QT first. Now we can go on and get the value for QT. So what will be QT? So let us look at, for QT, it will be equal to, let us look at QT. QT is equal to negative 1 plus 2 lambda. We are going to substitute lambda here. So that is negative 1 plus 2 lambda. That is 1 plus lambda. Negative 2 plus 2 lambda. So this is the one we are going to substitute in. Now, what is our lambda? Our lambda is 5 over 9. I hope we have negative 1, 2 plus 2 lambda, 1 plus lambda, negative 2. Okay, it is okay. So we are substituting, we are going to substitute 5 over 9. So when you substitute 5 over 9, you have negative 1 plus 2 times 5 over 9, 1 plus 5 over 9, negative 2 plus 2 times 5 over 9. So let's simplify that. So this is same as having negative 1 plus 10 over 9, 1 plus 5 over 9, negative 2 plus 10 over 9. What will this one be equal to? This will be negative 9 plus 10, which is 1 over 9. This will be, LCM will be 9 times 1, that is 9, that is 14 over 9. This will be negative 18 plus 10, which is negative 8 over 9. So that is what we shall have. Now from this, we can pull out the 1 over 9 is common. So 1 over 9, what shall we remain with here? 1, 14, and negative 8. So this is our QT, vector QT. Now, vector QT, as I said, will act as our parallel vector, because the line that is passing through Q to Q, this one here, this line that is passing through Q is parallel to the vector Q to what? Q to T. So if it is parallel to the vector which is Q to T, it means if we know Q to T, then we can easily get what we call the parallel vector. And then we substitute in this equation using A. A is a point that is on the line. The point is this. Then vector B prime is the parallel vector which we are taking as QT. So that is what we shall consider there. So now we can write the equation, but before that we can now put this note. So now the vector parallel, now the vector parallel to the required line, must be parallel to QT. It must be parallel to QT. So therefore, the vector parallel, therefore the parallel vector or the vector parallel will be, therefore the vector parallel is, as we said last time, whenever we are taking the direction vector or the parallel vector, we take this one, the simplified one, okay? So the simplified one is the one that you consider. So the simplified vector there is 1, 14, and negative 8. So is 1, 14, negative 8. So that will be the parallel vector. So now for that case, we have the parallel vector. We know the vector which is on the line. So now we can get the equation of the line. So the vector on the line is this. The point on the line is this. The parallel vector is what we have got here. So now let us get the required equation. Now the vector parallel to the required line must be parallel to QT. Therefore, the vector parallel will be that. Now, from vector R, which is equal to A plus lambda vector B, let us take that one there and that one there. So our A parallel is the point on the line, and that point is the point Q. This point here, 2, negative 1, 4. 2, negative 1, 4. Then B prime is our parallel vector, which we are taking as 1, 14, and negative 8. So from that, we should be able to get the required equation. So the required line equation will be R, which is 2, negative 1, 4, plus, we can use another parameter other than lambda, because lambda here, it was there. So let us use another parameter there. Maybe we can choose another parameter like mu. So this will be mu. B prime is 1, 14, and negative 8. So that will be what we call the equation of the line. So that will be the equation of the line. Now from that equation, they also wanted us also find the distance of Q from the line given. So what will be that? What shall we do there?
Magnitude
We take magnitude of
magnitude of B prime.
B prime. Taking the magnitude of this.
Yeah.
This is the direction vector. When you take the magnitude, it might not give you the required answer, because for this this is the direction vector. So, but the magnitude now you need to take for QT. QT is this. Remember, out of QT is where we obtained this, but we never use the 1 over 9. But for this case, in the magnitude, 1 over 9 is important, because this is describing the direction. So for the direction, you are not interested in the magnitude of the value. You are interested in the direction. So that's why for the direction, you can take this, or else someone can take the way it is here. You will all get the same answer. But for the magnitude, you have now to take this, because we need this distance here from this point to this. So it is same as getting the magnitude of QT. So what we need to do here is to get the magnitude for QT. So for the distance, we shall take the magnitude of QT. So your QT is this one here, is this. So that is 1 over 9. As I said, if you already have the square outside, maintain it. Then take the square root of this remaining one. 1 squared, 14 squared, negative 8 squared. You will excuse me a bit. So that will give us 1 squared plus 14 squared plus negative 8 squared. That is what we shall have. 1 squared, 14 squared, negative 80 squared. We are taking the magnitude of this. So that will give us the required answer. So that will be 1 over 9. Then square root of
261.
261. So you can now get the answer, and this will be units. So that will be the required answer.
1.7951.
1.7951.
7951.
7951. So that will be the required distance. So that will be answered. So that is about the perpendicular distance of a point from a given line. And in our next lesson, we shall be talking about intersection of lines in a three-dimensional space. So for today, we can now stop there.
Okay.
You first observe those ones.
Yes.
First observe. Actually, there is this this item that you should at the moment be able to do. So at the moment, you should be able to try this item. I pressed it in the other group, so I don't know if you have seen it.
Yes, let me check.
I don't know if I sent it or I didn't. I'm not sure. But what I know, maybe I pressed it in the other group. This one of.
Basics mathematics.
I doubt if I sent it there. Let me try maybe to send it. It was on my channel. Let me try to send it. I think I had not yet sent it in that group. So let me forward it there. So at the moment, you should be able to try this because it is for the concepts that we have already talked about, especially getting the coordinates for a point that is lying on a straight line. Also, it is talking about also it is talking for pick this one. Is also talking about this same thing that we have looked at, which is for distance of a point from a straight line. So now this item should be easier for you. So I'm going to forward it in the group so you can try it out. Is my screen visible?
Yeah, it has come.
Okay. So yesterday we were looking at how we can get the perpendicular distance from a given point to the line. Where we looked at also how best we can use the formula for obtaining the perpendicular distance. Sometimes it is called the shortest distance from a point to the line. So having looked at that, I want us now to look at the intersection of lines. I want us to talk about the intersection of lines in a three-dimensional space. So that is what we shall be talking about. Intersection intersection of lines in a three-dimensional space. So when we are looking at a two-dimensional space, if two or more lines intersect, then it means there exists a point whose coordinate satisfies the equations of all the involved lines. You have been solving that. You are given two equations and you solve the two equations simultaneously, isn't it? You have like 2x plus 3y is equal to 5. You have
Yes.
maybe x minus y is equal to -2. You have such equations. So this is an equation in a two-dimensional space.
Mm.
So as in a two-dimensional space, when you are told that these two lines intersect, then it means there exists a point of intersection, x and y, which satisfies this equation and this equation. So which means that if the equations of the intersecting lines are, for instance, in a given in a vector form, for the case when we are looking at a two-dimensional space, then it means again there exists a solution for the scalars, which gives rise to the same point upon substitution in all their respective equations. So meaning that we shall be saying that if two lines, for example R1 and R2, meet, then at the point of intersection, line R1 will be equal to line R2. So that is basically what we shall be talking about. So in general, we shall be saying that if two lines, for example R1 and R2, for example R1 and R2 meet, if these meet, then at the point of intersection, at the point of intersection, it means that R1 must be equal to R2. If two lines, that is R1 and R2, meet, then it means at that point of intersection, the two lines will be equal. So mathematics, we don't overtalk. We shall look at examples. We see how best we can get
Okay.
at the point of intersection if two lines meet. So we shall look at our example one, which says that lines L1. Let us have this. Line is L1 and L2 have a vector equation. Have vector equations. We have R1, which is -2, 8, and -1. We are adding there lambda into 1, 3, and -2. And we have R2, which is equal to 8, -1, and 3, plus mu into -4, 1, and 0. So we have got these lines L1 and L2 with these vector equations R1 and R2 equaling to that, respectively. So what we need to show is, we need to show that L1 and L2 intersect. And then you find the position vector, and you find the position vector of their point of intersection. So this is what we want to look at. So we are given two lines, L1 and L2. And these two lines here, we are told that these two lines intersect. And if they intersect, we need to show that whether they are intersecting. And then after we find that point of intersection. But the point that is required is the position vector of the point of intersection. Now we shall suppose that these points here are intersecting at a given point. So let us look at the solution. We shall suppose that the lines we suppose that the line is L1 and L2. L1 and L2 intersect at a given point. For example, that. So that is our assumption. Suppose that the line is L1 and L2 intersect at point T. Then what does that imply? That means that at point T, R1 will be equal to R2. Because we are told that we have R1 and R2, and we need to show whether these are intersecting. So at the point of intersection, that is what we are supposing. Suppose that the line is L1 and L2 intersect at the point T. So it means if they intersect at point T, then this R1 must be equal to R2 from even what we said here. Because if the two lines intersect, then at the point of intersection, they must be equal. So likewise, we shall do the same here. So if R1 is equal to R2, that means that we shall have -2, 8, -1, plus lambda into 1, 3, and 2. So this must be equal to R2, which is 80, -1, and 3, then plus mu into -4, 1, and 0. That is what we shall have. Now from here, our main task will be to get the values for lambda and mu. That will be our first main task. So let us look at that. So from this, we can easily see that here we can add the corresponding components. -2 plus lambda, this is 8. 8 plus 3 lambda, -1 plus 2 lambda. So this must be equal to 8 minus 4 mu, -1 plus mu, then lastly 3. That is what we shall have. Now let us equate the corresponding components. So let us equate the corresponding components. So we shall say equating the corresponding components. We shall be able to have -2 plus lambda, which is equal to 8 minus 4 mu. And this implies that we can form an equation. Let us bring this one this side. Lambda plus 4 mu, which is equal to, bring this one the other side, that will be 10. We can call this equation 1. Let us get 8 plus 3 lambda, which is equal to -1 plus mu. And this will imply that 3 lambda minus mu is equal to -9. That will be equation number 2. And lastly, -1 plus 2 lambda is equal to 3, which implies that this is 2 lambda. We take -1 the other side, it becomes 4. And clearly, we can easily see lambda is same as 2. So we have got lambda as 2. We need to substitute this lambda and get the value for mu. So let us substitute. So substituting lambda equaling to -2 into equation, we can use equation 1 or equation 2. So let us use equation 1. So we shall have 2 plus did we pick this one well? This is supposed to be -2. So let us change that one there. This is supposed to be -2 here. So this is -2, giving us here still -2. Let us make that, giving us here -2 still. So meaning the value will be negative, this will also be negative. So when we substitute actually lambda equaling to -2 into equation 1, we shall be able to have, so in equation 1, what shall we have there? So equation 1 is lambda, which is -2 plus 4 mu, which is equal to 10. So it means 4 mu is equal to, is it 12? So giving us mu as 3. So after getting mu and lambda, then there is one equation that we have not used. There is one equation that we have not used. Which equation is that? That is equation number 2. So after you have got the values for lambda and mu, you must substitute it in equation 2 and see whether it satisfies that equation. Then if it satisfies all the components of the equations that you are having, then those values will be true. So it means the point of intersection exists. But if they don't satisfy the other equation, then just know those lines don't intersect, and that point of intersection will not be existing. So that is how, because it's possible you can get lambda here and mu, but when they are not satisfying the other equation. So you must also test.
So do you use the equation that you did not use for finding lambda?
No, for getting lambda, you will use two equations, because looking at 3 dimensions, it means you will have 3 equations. You have this equation, and this. But when you are to get lambda and mu, you use 2 equations. But there will be one equation that you will not use. So that one equation that you will not use is the equation you will use to confirm whether the values of lambda and mu holds. Then from there you get the point of intersection, meaning that don't get the point of intersection before you have substituted this mu and lambda in the equation you have not used. Okay, so that is what we want to look at. So let us substitute. Now let us substitute, also substituting lambda equaling to -2 and mu equaling to 3. So substitute this into the equation you have not used. Into equation, was it equation 2? Remember here we used equation 3, this equation here, which was equation 3, to get the value of lambda. And then from that we substituted it in equation 1 to get the value of mu. But we have not yet used equation number 2. We have not yet used equation number 2. So the equation number 2 will be to help you confirm whether these values are satisfying that component as well, or that component equation. So let us substitute that into equation number 2. Basically, you are testing, you are trying to test for consistency, meaning that lambda and mu that you have got must be in position to satisfy that equation. So our equation is 3 lambda minus mu. So from 3 lambda minus mu, which is equal to -9, is equal to -9. So what will be 3 lambda minus mu? This will be same as 3. Lambda is -2 minus mu is 3. So this is same as 6 minus that, which will be 9. So clearly, it implies -9 is equal to -9, isn't it?
Yes.
So that one holds. So if it holds, now you can give your conclusion that says the values of lambda and mu obtained hold for all the three component equations. Then the given lines intersect. So meaning that you will be able to say that the lines intersect only when the values for lambda and mu you have got satisfy all the three components, all the three components here. All the three equations must be satisfied for the values of lambda and mu. So it means that part 1 show that L1 and L2 intersect will be answered. Because here we started by saying suppose that the line is L1 and L2 intersect. So, but we are not sure whether they intersect. So what confirms that is when you get the values of lambda and mu and you realize that they satisfy all the three vector components that you have. So there you will say that they are intersecting. But now if they intersect, then they must be intersecting at a particular what? At a particular point, isn't it? Yes. So that point is the point of intersection that we want to look at now. So let us look at the point of intersection. First of all, we said that suppose these lines intersect at point T. So it means at point T, that is where we are having at the point of intersection. So let us say now we need to obtain the point of intersection. To obtain the point of intersection, use any of these lines, either L1 or L2. So you can use this one here, or you can use this, because mu and lambda satisfy all the equations. So you can use R1 for example. So our R1 is that. So we shall say using line 1, where we are having lambda as -2. So our lambda is -2. So we want to substitute this lambda here. Someone can use this one here, this R, and you substitute for what? For mu. You will all get the same answer. So let us use L1. So L1, it was R, which was equal to, it was -2, 8, -1, plus lambda into 1, 3, -2. So that is what we had. We confirm -2, 8, -1, 1, 3, -2. Okay, now it will imply that at point t, it means this t will be satisfying this, so we shall have the position vector for t equaling 2. So -2, 8, -1, plus lambda is -2. So put it into that 1, 3, -2. So this will give us, so this is -2 minus 2. This is 8 minus 6. This is -1 plus 4. So which will be -4. This is 2. This is 3. So this will be our position vector t. That is at point t. And have it as position vector t or ot, because we are saying the point of intersection is occurring at point what? At point t. So what we wanted is we want the position vector of the point of intersection. So it means you will give your conclusion that therefore the position vector of the point of their point of intersection is, so we shall have -4i plus 2j plus 3. Okay, please always recall that whenever they are talking about the vector, it has to be either in the column form or in this form. So if you simply say the position vector of their point of intersection, then you put -4, 2, and 3. This one becomes wrong. This is the coordinate form. So this is a point t. But now we need the position what? We need the position vector. So the vector is either written in this format of I, j, and k, or else in the column form. So that is how we write what we call the position vector. So I hope the procedures are clear.
Yes.
So that is basically what we shall be having when we are to look at the point of intersection. So at the point of intersection, the two lines will be equal, and if they are equal, get the values for lambda and mu, or for the scalars. After doing that, then substitute for either lambda in any of the equations of the line. But also you need to recall that whenever you get the values of lambda and mu, to conclude that they intersect, then those values must satisfy the other equation that you have not used. So that is our example number 1. So from that, we want to look at our example number 2. It says find the point of intersection. Find the point of intersection. Find the point of intersection of the lines. We have x minus 5 divided by 4, y minus 7 divided by 4, z plus 3 divided by -5, and x minus 8 over 7, y minus 4 over 1, z minus 5 over 3. Can we look at the point of intersection of that?
Okay.
So let us look at the solution. So to look at that, let us begin by looking at this. Let x minus 5 over 4 be equal to y minus 7 over 4 be equal to z plus 3 over -5. Let this one be equal to a scalar, maybe mu. Then with that, what will be x, y, z in vector form? I hope now you should be able to get that one out. So this is representing our R now for our case. What will that one be equal to?
5, 7, negative 3.
5, 7, negative 3. Good. Then plus our scalar, we are using that. Mu into
4, 4, negative 5.
4, 4, negative 5. That is what we shall have. So we can have this one as our R1. So this will be 5, 7, negative 3. We add there mu, which is 4, 4, negative 5. So I want us to call this one equation number 1. Likewise, I want us to let the other equation, which is x minus 8 over 7, y minus 4 over 1, z minus 5 over 3. We let this to be equal to another scalar like that. So what will be x, y, and z? So x, y, and z will be equal to
8, 4, 5.
8, 4, and 5. Then plus lambda into
7, 1, 3.
7, 1, and 3. So it means we can rate this to be our R2, which is 8, 4, 5, plus lambda into 7, 1, and 3. We can call this one equation number 2. So we want the point of intersection, and at the point of intersection, it means R1 must be equal to R2. So we shall suppose the lines intersect at point T. Suppose these intersect at point T. Then what does that mean? Then at that point T, R1 will be equal to R2. So if R1 is equal to R2, we shall have 5, 7, negative 3. We shall have mu into 4, 4, negative 5. We shall have this equal to 8, 4, 5 plus lambda into 7, 1, and 3. So from that, our interest now is to form the equations in terms of lambda and mu, and we solve them. So from here, can I get these equations at once? I hope it will be okay. This is 5 plus 4 mu, which is equal to. So here we are equating. I am equating this at once, equating the corresponding. So I'm equating the corresponding component vectors. So let us do that. So 4 plus 4 mu is equal to 8 plus 7 lambda. Which implies that 4 mu minus 7 lambda is equal to, I'm bringing this, taking this one to the other side.
3.
That is 3. We call this one equation 2, equation 3 now. Equation 3. Let us have another one, the y component. We have 7 plus 4 mu, which is equal to 4 plus lambda. This will imply that 4 mu minus lambda is equal to negative 3, equation number 4. And next we shall have negative 3 minus 5 mu is equal to 5 plus 3 lambda. This will imply that negative 5 mu minus 3 lambda is equal to 8. So we can have this as equation number 5. So now with these equations, which ones can we easily consider and solve easily to get the values of mu and lambda?
3 and 4.
So we can easily consider 3 and 4. So let us consider equation 3 and equation 4. When we consider 3 and 4, we shall have 4 mu minus 7 lambda, which is equal to 3. 4 mu minus lambda, which is equal to negative 3. So from here, we shall subtract. Let us remove this mu. So this will give us negative 6. Is it?
Yes.
negative 6 lambda, which is equal to 6, giving us lambda as negative 1. So having gotten the value for lambda, let us substitute this lambda here, which is equal to negative 1, into equation, which is equation number. We can use any of the two equations we have used. Equation number 3. Let us use equation 3. So we have 4 mu minus 7 into negative 1 is equal to 3. So this is 4 mu plus 7 is equal to 3. 4 mu is equal to 3 minus. So 4 mu is equal to negative 4, giving us mu as negative, giving us mu as negative 1. Now we have got the values for lambda and mu. But remember, our interest is to show that these points here, it is to show that these points intersect. And if these points intersect, then it means the values for lambda and mu must satisfy the equation we have not used. Which equation didn't we use? Equation 5?
Yes.
Equation 5. So let us substitute. A lambda equaling to negative 1 and mu equaling to negative 1 into equation number 5. When we substitute lambda and mu into that equation, we have negative 5 mu. So let us say from negative 5 mu, was it minus 3? Minus 3 lambda, which is equal to negative. It's negative, positive 8. So this will give us negative 5 into negative 1 minus 3 into negative 1. So this will be same as 5 plus 3, which is 8. So it is clear that 8 is equal to 8. So clearly it satisfies. So now we can conclude that since the values of lambda and mu obtained hold for all values, hold for all the component equations, hold for all the component, hold for all the component equations, then the given lines intersect. So that is what we shall conclude, that these lines here truly intersect. After that, can we now use any? Remember, our question is we need to find the point of intersection. So what we have shown is that the two lines intersect, but we must get the point of intersection. So we shall use any of these equations, either equation 1 or equation 2. So which one should we use? Equation 1. So using equation 1, you write for me this equation somewhere so we can refer to it. You have it?
Let us use 2.
Equation 2.
Yeah.
Okay. So you put it. You put it down.
8, 4, 5, 7, 3. Yeah.
Okay. So we shall say.
R2.
We shall say from or using. Let us say using
equation 2.
Equation 2, which is given as R2 equaling to
845.
845.
Yes.
Plus
lambda into 713.
713. So let us substitute for lambda, which is equal to negative 1. It was that. Okay, negative 1. So that will give us, that implies that at point T, remember that was at the point of intersection. So at point T, it will imply that the position vector T will be 8, 4, and 5 plus negative 1, 7, 1, and 3. So this will be able to give us 8 minus 7, 4 minus 1, 5 minus 3, which will be same as 1,
3, 2,
3, and
2.
1, 3, and 2. So, but what are we asked? We are asked to obtain at the point of intersection. So now the point of intersection will be, so we conclude now, therefore, at the point of intersection, the point of intersection of the lines is, now you will give it as 1, 3, and 1, 3, and 2. So now don't give it as I plus 3j plus 2k. Okay? So you must know where to use this one and where to use this. For this one, it represents simply a point. The moment you say a point A is 1, 3, 2. You use it in coordinate form. You represent it using coordinate form. But for if you are to talk about the position vector of A, then you don't write it as 1, 3, 2. This will be wrong. The position vector of A is written as I plus 3j plus 2k. So long as it is now a vector, position vector, or it is vector A, you either put it in the column form or put it in the I and jk format. But if it is simply a point this, then put it in the coordinate form.
Okay.
So that will be the required answer there. So that is about the point of intersection. So we shall try example number 3, which says that find the equation. Find the equation. You will be the one to take us through that. Find the equation of the line. Find the equation of the line through A, which is 2, 2, and 5, and B, which is 1, 2, and 3. That is part A. And B is if the line in A above meets the line which is x minus 1 divided by 1, y minus 2 divided by 0, z minus 1 divided by 3. At P, find the coordinates. Find the coordinates of P. So you will take us through that question there.
So, according to the first question, we are finding the equation of the line passing through the points A and B. So we are going to use the formula R equals to A vector A plus lambda vector B.
So we shall use R is equal to A plus C
plus lambda vector B.
Vector B.
Yes.
Then
our R is, we're going to let our R be X, Y, Z.
Let R be X, Y, Z.
Which is equals to, our A is 225.
Our A is 225.
Minus lambda into the B is 123.
And the B is
1,
2, 3.
Yes.
Oh, you man, where did we say this one from? They are saying find the equation of the line through A and B. So you are telling us that this B, which is a point through which this line is passing, is the parallel vector. Because this B represents the parallel vector. So
no, sir. Which formula are you supposed to use?
I'm also asking you.
Are you going to use the normal way of finding? Oh,
the normal way of finding what?
A point on a line.
Which way is that one again? Man, we have studied about these things. We haven't even finished the day. We talked about how to obtain the equation of the line. If you recall, we talked about 2 ways how a line can be defined. What was the first one? Actually, there are 3. The first one was?
Vector equation.
No, those are the forms, how the line is defined. One, we looked at if you are given a point and you have a parallel vector. You are given a point, you have a parallel vector. Let me write it here. You are given a point, if you recall, you have a line. This was the first part. You have a line, you have a point on the line, you have a general point on the line, you have the parallel vector to the line. And this was defined to the origin. This was also defined to the origin. This was defined by R. This was defined by position vector A. Here we said that here we use R, which is equal to vector A plus lambda vector B. B is this parallel vector. The vector which is parallel to this line A that is passing through the point A. This R is a general point. We said this. This is one form. We looked at another one where you are having a line that is passing through 2 points. If you recall very well, we said that if you have 2 points, A and B, and these ones here are all defined from the origin. So meaning that we have this as position vector B, and this as position vector A. But on this same line, we have what we call a general point, which is R. This is defined by vector R. We said that this line R, actually we said that for this case, AB and AR are parallel. AR is parallel to AB. We also proved this one. We said AR is the same as lambda AB. We said that this is OR minus OA, which is equal to lambda AB. We said that OR is same as OA plus lambda AB. We again said this is vector R, which is equal to vector A plus lambda vector B minus A. We said that so long as you are having 2 points, you are having a line passing through 2 points, A and B, then the vector A to B will be parallel to the vector A to R because they are in the same direction. And even they are even on the same line. So you can easily say that they are collinear. We looked at this. And we also talked about this. That is R is equal to A plus lambda B. Where did this one come from? We proved that. We said that this vector A to R is actually parallel to vector B, this vector. What does that imply? That OR minus OA is same as lambda vector B, meaning that R minus vector A is lambda vector B. In other words, when you take this one, the other side, you get R, which is equal to this. This one is the way you define a line if you are having only 1 point. So they tell you find the equation of the line passing through vector, passing through point A, and is parallel to the vector you are given that. You use this. If they give you 2 points, find the equation of the line through A and B. You are given 2 points. What do? If you are given 2 points, then you use it. Your parallel vector becomes what? Becomes AB, isn't it?
Yeah.
Your parallel vector becomes AB. So here what you are telling me is that this B, which is even given as a point on the line, for you are taking it as the parallel vector. Those are two different things. Now, we also, if you recall very well, we also talked about that in some incidences, you are given 3 points, A, B, and
C.
We also said that sometimes you are told to find the equation of the line that is passing through 3 points, A, B, and C. And the first thing we said is that the moment they tell you this, you must first of all show that A, B, and C are collinear. In other words, they lie on the same straight what?
Line.
On the same straight line. By either getting AB is can be expressed in terms of BC. If you are able to find that AB can be expressed in terms of BC, then it means that you will use your R, which is vector A plus lambda vector BC. You can also use your R as A plus lambda vector AB. You can also use this. You can also use this because, after all, the AB can be expressed in terms of BC. So here you can use BC or you can use AB. This is when you have 3 points. But the most important thing is you must first of all show that they are collinear, which is not the case when you have only 2 points. Now you have forgotten all those ones there.
I have forgotten this second one here.
Let me see where even we talked about that. This one is not there. You might say that we never talked about it.
That one we talked about it, but I had forgotten about it. I only remember the first one and the third one.
So you must recall these things here and also know how they come about. Know how you can easily get it. Even if you forget, know that if I have 2 points, what happens? If there are two, if it is only 1 point, if it is only 1 point, you are given the parallel what? You are given the parallel vector. If there are 2 points, then you are the direction vector or the parallel vector is AB. So now let us answer the question now.
So now, our formula is
so
vector R equals to...
you first put this question down there.
The points, eh?
No, the whole question.
Part B or the whole question?
The whole A and B.
Okay. Done.
Done?
Yes.
Okay, so let us look at now the solution.
So part A will be vector R equals to vector A plus lambda into vector B minus vector A.
Okay, let us maintain AB.
Yes. So we find AB.
So
Vector
find AB. So what is A?
A is 225.
225. What is B?
B is 123.
123. So let's get AB.
123 minus.
That is OB. Define it very well. So this will be 123
minus 225.
2, 2, and 5.
So it will be -1, 0, -2.
-1, 0, -2.
Yes. And we come and now plug in the values of A and the B. AB. So our A is
there is something you haven't done for me still there. There is something you haven't done for me still on reaching here. What will be your parallel vector? Because you are taking your AB as a parallel vector, there is something you need to do here. What is that?
Is it placing in a coordinate form?
No. When you reach here, whenever we are taking the direction vector or the parallel vector, we take the simplified form. You recall that. I remember telling you that customary, it is always important that when you are taking the component, the parallel vector here, either this one should be positive or it should be the simplified form. So here there is something we can pull out, which is -1. So it is always important this value here to be positive. So this is 1, 0, and 2. Okay?
Yes.
So this implies that your parallel vector is 1, 0, and 2.
So in negatives, it is not simplified.
No, here it is still not yet simplified because we can simplify it and have it as this. Okay. So when you have it, if it can be, if you can pull out the scalar, it is okay. But if it is a negative for this one here, especially for the I coordinate, then what we do is to make sure that we make this one positive. I remember giving that note somewhere. Let me see if I can get that. Don't know if it was in this part. Okay, let me get the one for the line. Okay, this one we already have it. Lines. Must be here. Okay, let's check here. What we are talking about in a situation where 3 points lie on the line. Okay, I need where I place that note. Do you see that?
Yes.
Customarily, the vector parallel or the direction vector is usually in its simplest form, and the coefficient of I, if n being what?
Positive.
If the I is there, if the I component is there, then if possible, make sure that that component is positive. That is what we talked about last time. The vector parallel or direction vector is usually in its simplest form. If it can be simplified, make sure you take the simplest form. And the coefficient of I, if it is there, it should be what? It should be positive. So you need to be recalling some of these things here. So our parallel vector is this 1, 0, and 2. Okay?
Yes.
Now, can we go on?
Yes. So our R,
Our
R equals to vector A is 2, 2 to 5.
Is 2, 2, 5 plus
2 to 5 plus lambda into -1, 0, negative. No, +1, 0, +2.
So we are there.
Yes.
So that is the R. What do we need? We needed find the equation of the line. Find the equation of the line that is passing through. That word should be there, passing through A and B. Okay. So that one will be answered. Then part 2. Part 2 we need if the line in A above meets the line this one here at a point P, find the coordinates of P. We move on. After this, what
Since we
have?
Since you have that, we shall have it as equation 1.
Okay. So we shall relate. We can relate it maybe to be R1, which is 2, 2, and 5, plus lambda into 1, 0,
1, 0,
and 2. This one to be equation number 1.
Then in part 2, we have to extract equation 2 from this given line.
So we are given x minus 1 over 1.
X minus 1 over 1 equals to y minus 2 over 0 equals to z minus 1 over 3. Yes.
So we must equate this to a given scalar as well, such that you get the equation. So can we maybe use mu?
Yes. So our R will equals to
this is R1, let this one be like R2.
R2 equals to 1, 2, 1. 1 to 1 plus mu into 103, which will be our equation 2. Then from here, since you're saying that
They are saying that if the line in A above meets the line that at P.
If they meet, which means that they must intersect. So we equate equation. We have to equate equation 1 to equation 2. So R1 equals to R2.
That is where you need to be telling the person who is following your work. R1 is equal to R2. What statement do we need to put there before that?
Since the line A meets since line R meets R2,
so we are saying that since that one meets the other one, then
they intersect.
Hey, you haven't shown that they are intersecting. You need to first of all show that they intersect. And if they intersect, then you get the point of intersection. Because there it is not a must. Okay, they are saying if the line in this one meets this line at P, they can be meeting, but when they are when there is no, the point of intersection is not satisfied. So you must show that if they meet, they are intersecting at a given point. Okay, so we can say at the point of intersection or at the point of their meeting. That is what it means. So at point of intersection. So the point of intersection was given as what?
As
P.
Yeah.
So at point of intersection P, then R1 must be equal to R what? Must be equal to R2, isn't it?
Yes.
Okay, so let us equate the two. So we are having
225 plus lambda into 102 equals to 121 plus mu into 103. Then here we add in both sides we add 2 plus
equate.
lambda.
We are equating the corresponding vector components. So we have 2 plus
lambda. 2 plus lambda equals to 1 plus mu. Then 2 plus 2 equals to
no, let us first simplify this.
This one will be
lambda minus
mu equals to -1. Then here it will be 2 equals to 2 plus.
This is 0. 2 is equal to 2 plus 0 also. Isn't it?
Zero equals to 2 plus 0.
So which will be 2 is equal to 2. Next.
2 lambda equals to 1 plus 3 mu.
Which implies that?
Which implies that 2 lambda minus 3 mu equals to -4.
So this one is already holding 2 is equal to 2, which means whatever values we get here will be satisfying, isn't it? Yeah, that equation is already holding here, 2 is equal to 2. So it means they are already intersecting. So let us see.
Solving
equations.
Equation 3 and 4 simultaneously.
So from equation 3 and 4, we shall have lambda minus mu is equal to -1. 2 lambda minus 3 mu is equal to -4. So we interchange and we subtract. So what shall we have? 2 lambda minus 2 lambda is 0. That is negative. This is minus 2 mu minus 3 mu, which is plus 3 mu, which is equal to
1 plus 4.
We are multiplying by 2. Negative 2 plus 4.
Yes.
So this is a negative mu, which is equal to?
It is mu.
It is positive, eh? Okay.
Yeah.
So which gives us mu as mu as 2. So we have got mu. We need the lambda as well. So which one can we substitute in the third equation?
Yes.
So from lambda minus mu, which is equal to negative 1. So lambda minus 2 is equal to negative 1, which gives us lambda as positive 1.
Yes.
Positive 1, negative 1.
Positive 1.
Positive 1.
Yes.
Okay. We go on. So we need, now it is already true because 2 is equal to 2. So you cannot now substitute in this. So it means the two equations are already intersecting. So now let us get there. What are we required to get? Coordinates of P. Remember, P is the point of intersection. So which line are we using?
These are R2.
So let us say at point P, so the position vector P will be equal to, let us refer from R2. So what was R2?
R2, 1, 2, 1.
1, 2, 1.
1, 2, 1 plus mu into 1, 0, 3.
So what will be P, vector P? So vector P will be, let us substitute for mu. What was mu? Mu was 2.
Yes.
Mu was 2.
Yes.
Okay. So let us substitute that. So this is 1, 2, 1 plus 2 into 1, 0, 3. So this will give us 1 plus 2, 3. This is 2, 7. So which means the point of intersection P is
3, 2, 7.
So that will be at the point of intersection. So that one will also be done. Okay. So that one will be done. So you will try for me this question here. I haven't seen the ones you took yesterday. As if yesterday I gave you some. You want them to first become many?
You didn't give yesterday?
Yes. Let me check here. Yesterday, even in this, as if it is even here. Yesterday, these were the questions I remember. Because we stopped on this. Let me see. There was this question. Where I said you need to use the two methods. because later we did this one together, this part, but this one is still there. So make sure you put it down and you don't forget it this time around.
Okay. Yes.
Done?
Yes.
Okay. Make sure whatever concepts we finish, you go on and try those numbers out. So I want you to try this one as well. So the question says, the vector equations of two lines are, so we have R1, which is equal to 2I plus J plus lambda into I plus J plus 2K. And we have R2, so we are given that the two lines intersect. So you need to find part one, the value. You need to find the value of t, and two, the coordinates of the point of intersection. So that is what you need to find. So put that one aside as well,
Yes. I'll put.
and you try it out. So after that, we shall look at another part that is for parallel lines. So we want to talk about Last time we talked about parallel vectors. So this is what we want to talk about. We want to talk about parallel lines and skew lines in a 3D space. So if two lines are such that their direction vectors are themselves parallel to each other, then the two lines are said to be parallel. So we shall be saying that two lines are parallel if their direction vectors are also what? Are also parallel. So that will be the condition we shall be using. So we shall be saying that if two lines are such that their direction vectors are such that their direction vectors are themselves parallel to each other, then the two lines are also parallel. So you'll be able to say that two lines are parallel if their direction vectors are what? Are parallel. So that is the condition we shall be using. Now, for such direction vectors, they are either equal, or one vector can be expressed as a scalar multiple of the other, or one vector is a scalar multiple of the other. So that is for parallel lines. We shall be using the same conditions we used when we are looking at parallel vectors. Two vectors are said to be parallel if you are able to express one as a scalar multiple of the other. That is about parallel vectors. But parallel lines, you will say that two lines are parallel only when their direction vectors are what? Are parallel. So which is the most important thing here is to first know how to extract out the parallel vectors, then test whether they are parallel to one another. If they are parallel to one another, then conclude that the lines are also parallel. Then the next one we want to talk about is the skew lines. What are the skew lines? We shall be saying that two lines are skew if they are neither parallel nor intersecting. Such lines don't lie in the same plane, and therefore they are non-coplanar. So that is what we shall be using. So two lines are skew if they are not parallel and if they are not intersecting. Meaning, if you are to show that the two lines are skew, you must test whether they are parallel, you must test whether they are intersecting. If they are not parallel and they are not intersecting, then you conclude that they are skew. And then for parallel lines, those ones you know how to deal with that. So we shall also talk about some examples as well. So let us look at some of the examples. So we shall begin with example 1, which says show that the lines R1, which is I minus j, plus T1 E2I plus 2j minus k. And R2, which is 2I minus plus j minus k, plus T2 E2 negative 2I minus 4j plus 2k. Show that the line is R1, which is equal to that, and the R2, which is equal to that, are parallel. So what should we do? From what we have seen about parallel lines, what should we do?
We should
I take you back to the conditions. This is what we said here. So from that, what should happen?
one is a scalar multiple of the other.
So what should we do here for this question? Because last time we talked about parallel vectors. So
This one I have no idea.
hey, from this same statement, what does it say? If two lines are such that their direction vectors are themselves parallel to each other, then the two lines are also parallel. So when they tell you show that these lines are parallel, what exactly are you supposed to do?
Extract the direction vectors.
Get the direction vectors, see if they are parallel. If they are parallel, then you conclude that lines are what?
Parallel.
Lines are parallel. As simple as that. So can we extract out the those direction vectors? So let us look at the first line. So the first line is parallel to.
Oh, I'm not getting you.
I'm saying the first line is parallel to. What is the parallel vector there? Your network is not good.
Yeah, I'm not getting you well.
I was saying we need to show that these lines are parallel. And if the lines are parallel, as we have seen from the definition here, if two lines are parallel, then you must first of all look at the direction vectors. So if the direction vectors are parallel, then you conclude that the lines are also what? The lines are also parallel. Okay? Are you getting me?
Yeah. Yes.
Now, so here we are given the two lines. Here we have the two lines, line 1 and line 2. So we are saying the first line is parallel to. What is the parallel vector to this line?
Parallel vector is 1, 2, negative 1.
1, 2, negative 1. This one.
Then
the second line is parallel to.
Negative 2, negative 4, 2.
So B2 is
Negative 2,
negative 4 and
2.
And 2. So you need to show that these words here can be expressed in terms of one another. So you can first of all maybe use the condition that either B2 can be expressed in terms of B1, then you check whether the values of lambda are consistent or are constant, or else you can look at the two. Can you express one in terms of another, looking at this and this?
Yes.
So if you consider For example, B2. Can we say B2 is same as -2, -4, and 2? And 2. That this one here is the same as, can we pull out which one? I want to create the relationship between this and this.
You pull out -2.
-2. So here we remain with 1, 2, and
1.
1, -1.
-1.
-1. So as you can easily see, this is -2, and what you are remaining with here is B1, isn't it?
Yeah.
So this implies that B2, vector B2 is same as -2, B1. Okay. So what does this one imply?
They are parallel.
It means B2 and B1 are parallel. And if the direction vectors are parallel, what should be your conclusion? Eh? So that will be the answer there. So long as you are able to show that B2 and B1 are parallel, then that will imply that the two lines are also parallel. So two lines are parallel so long as their direction vectors are also parallel. So which means you must first of all test whether the direction vectors are parallel. So if the direction vectors are parallel, then you can give the conclusion that the lines are also parallel. I hope you know another method of how you can show that this is parallel by using the one for lambda. So if you want, you can use that of the lambda, then you see whether lambda is constant. If lambda is constant, then you conclude. So you can first say for parallel lines or for parallel vectors, B2 should be able to be expressed in terms of B1, or B1 should be expressed in terms of B2. So put your B2 there, -2, -4, and 2 is equal to lambda into B1, 1, 2, -1. So get the value of lambda here. Lambda will be -2. Here lambda will be -2. Here lambda will be -2. So since lambda is constant, then clearly you can say that B2 is same as -2 B1, which means that vector B2 is parallel to vector B1. But in case you get different values of lambda here, then you conclude that the two are not parallel. Okay, so that is what was required there. So the next question, I hope this question is okay. Is that question okay? So we can look at another one.
Yes.
Okay, so part 2, we want to look at show that this is question 2. Show that the lines R, which is equal to 3I plus 2K plus lambda into I plus 3J plus 4K and the R, which is equal to -I plus 3J plus 5K plus mu into 2I plus J plus K as Q. We want to look at that. But before that, I want you to look at this condition as well. two lines are skew if they are neither parallel nor they are intersecting. Such lines don't lie in the same plane. Such lines don't lie in the same plane. In the same plane. And therefore they are non-coplanar. So we shall be able to say that two lines are skew only when we show that they are not parallel. Two, they are not what? Intersecting. So for you to show that the two lines are not skew, you must test for those conditions, two conditions. You must test for whether they are parallel, or you must test whether they are not intersecting. Okay? So by
Yes.
demonstration, when you are talking about skew lines and parallel lines, for parallel lines is you are having two lines. If two lines are parallel, it means this distance here is the same from one line to another. If these two lines here are parallel, if this line and this line are parallel, this is line 1, this is line 1, and this is line 2. So if they are parallel, then the distance is d1 is equal to what? If this is d1 and this is equal to d2, d1 is equal to d2. So it means that the points from any of the two lines are equidistant from one another. So the point from here to here is the same as the distance from here to here. So the distance will be the same. But if they are skew, it means they are not parallel and at the same time they are not intersecting. So they will be like this. So you are having one line there. So you have another line which is coming like that. They don't meet anywhere, but this distance here, this distance, and this one here, this distance are not equal. So you have like D2, you have this distance as D1. So D1 is not equal to D2. So the distance between them is not the same. So this is skew and this is for parallel. So they don't meet anywhere, they are not intersecting, but again, they are not parallel. So these are skew lines. So these are the parallel lines. So that is how we distinguish the parallel lines from the skew lines. Okay. So I want us to look at this question. I hope you are still there.
Yeah.
Okay. So our interest now to show that these lines are skew, we must first of all show that they are not parallel, and again we show that they are not intersecting. So we can look at that. So we need to deal with the direction vectors first for parallel. So let us test part 1. Let us first test whether the two lines are parallel. Let us first test whether the two lines are parallel. How do we do that? We shall get the position, the direction vectors. So let us get the direction vector for line 1. It will be B1, which is equal to
1,
1, 3, and we are taking this.
Yeah.
Then the direction vector for
L2.
For L2 is B2, which is
2,
2, 1, 1. So after that, we need to check whether we can express one in terms of the other. So
Okay.
let us suppose the two lines are parallel. Suppose the two lines are parallel. Then it means for a non-zero scalar, we are using lambda here. We can use any other scalar. Let's say alpha. It implies B1 should be expressed in terms of B2. So what is our B1? B1 is 1, 3, 4,
3, 4.
which is equal to alpha into 2, 1, 1. So this implies that 2 alpha is equal to 1. giving us alpha as a half. Here alpha is equal to 3. Is it a third? 3. This is alpha times 1, which is equal to 3. The next one, alpha is equal to
4.
Alpha is equal to 4. So we can easily see that the values for alpha are not constant. So we can say since the constant alpha takes different values, or you can say that since alpha is not constant, or since the constant alpha takes different values, then it implies that b1 vector b1 cannot be expressed in terms of a scalar multiple for b2, isn't it?
Yes.
So we cannot express b1 as a scalar multiple of b2. So therefore, the direction vectors are not what?
Skew.
Not skew.
Parallel.
The direction vectors are not parallel. And if they are not parallel, what does it mean?
They are not skew.
Hey, you like the word skew. If the direction vectors are not parallel, then it means the lines are also not.
Perhaps I thought they are asking us to say that to show that they are not skew.
Yes. But what are we testing first?
Whether they are parallel.
We are testing first whether the two lines are parallel. And how do you test the two lines are parallel? By looking at it, whether the direction vectors are what?
Parallel.
Are parallel. And if the direction vectors are parallel, what does it imply? That the lines are what?
Parallel.
Are parallel. So when after this does not directly mean they are skew. They are always skew when they are not parallel and when they are not what?
Intersecting.
Intersecting, yes, that's when you conclude. But at the moment, we are testing whether the two lines are parallel. And how do you test that? You first show whether the direction vectors are what? Are parallel. But we have seen the direction vectors are not parallel. And if they are not parallel, then it means the lines are also not what?
Parallel.
Not parallel. So that is 1. 2, we need to look at whether the two lines are what? Are intersecting, isn't it? So next 2, let us test whether the two lines are what?
Intersecting.
Intersecting.
So it is very necessary to test whether they are both parallel and intersecting.
Exactly. Before you give a conclusion, you must test for the two.
Okay.
You must test that they are not parallel or they are not intersecting. Because they can be parallel, you can test there when the condition for intersecting is happening. You never know. But for you to give a conclusion, you must test that they are not parallel and they are also not intersecting. So let us test whether the two lines are intersecting. Now we shall suppose that the two lines intersect. Suppose the lines intersect. Suppose the lines intersect at a point maybe T. Then it means at point T, so R1 will be equal to R2. What was this R here? So the first R was this, the next one was this. So can we extract out that? Let's extract out that because we want to equate them.
Okay. Yes.
You put it down?
Yeah.
Okay. So let us equate the two. So in that format, what will it be?
Will be 302. lambda into 134. 134.
Which is equal to
negative 135.
Plus
Mu into 211.
So we need to simplify this. So can we have this as it? Let us equate the corresponding components. Three plus lambda is equal to negative 1 plus. This is equal to lambda minus 2 mu, which is equal to, is it negative 4? 3 lambda is equal to, so this implies that 3 lambda minus mu is equal to 3. Lastly, 2 plus 4 lambda, 5 plus mu. Are you still there?
My mic was mute.
Okay.
I was talking, but things are not going.
Okay.
Yeah.
Now, let us now try to get the values of lambda and mu. We can easily consider 2 and 3. I think this is easier.
Yes.
So let us consider equation 2 and 3. So this is 3 lambda minus mu, which is equal to 3. This is 4 lambda minus mu, which is equal to 3. So if I want this, I will. What do we do here? We subtract.
Yes.
We shall subtract. So let us subtract there. So if you subtract, you will remain with?
You remain with the negative 4 mu plus 3.
Negative 4 from where?
If you multiply.
No, we are subtracting. We want to eliminate this.
Yeah.
So it becomes negative lambda. Negative mu minus minus is 0. 3 minus that will give us 0. So lambda is equal to 0. So let us look at from 3 lambda minus mu, which is equal to 3. So 0 minus mu is equal to 3. So mu is negative. Mu is negative 3.
Yeah.
I hope that is okay. So lambda is 0. Mu is negative 3. So remember, after solving that, we need to go back and substitute for. So we need to go back and substitute in the equation we have not used it. So let us test for consistency. Let us test for consistency in equation 3. For lambda equaling to 0 and mu equaling to negative 3. So are we using equation 3 or equation 1?
1.
Equation 1.
We use 2 and 3.
We use the 2 and 3. Okay. So equation 1 is lambda minus 2 mu lambda minus 2 mu, which is equal to
negative 4.
Negative 4. So For lambda minus 2 mu, this is lambda is 0 minus 2 e2 negative 3. This will give us 6. But 6 is not equal to negative. 6 is not equal to negative 4, isn't it?
Yes.
Hey,
True.
so if that one is not holding, then we shall now give a conclusion that the two lines are not what? Are not intersecting. So we shall say since the values of lambda and mu can't satisfy all the component, equations, all the component equations of the unit vectors, then the two lines don't intersect. Then the two lines don't intersect. Thus, can we give the general conclusion now? Since the given lines are neither parallel nor intersecting, they must be what?
Skew.
They must be skew. So that is now about the skew lines. So for you to test that those lines there are skew, then you must be in position to test for parallel and for the intersection. So that is about skew lines, parallel lines, and how to show that given lines intersect at a given point. Now, lastly, I want us to give a brief introduction about the distance between parallel lines. So how do you get the distance between parallel lines? As we have seen, that the distance between parallel lines does not change. That is the first fact. The distance between parallel lines does not change. So I want us to consider two parallel lines. Let us consider two parallel lines, L1 and L2, with equations R1, which is equal to A1 plus lambda vector B, and R2, which is A2 plus lambda vector B. As we have said, if two lines are parallel, then their direction vectors can be expressed in terms of one another. So that's why I'm maintaining this. So this one here, let us use mu. So I want us to consider these two lines. This is our line L1. This is our line L2. And we are saying that these two lines are parallel. So meaning that the distance between them, this distance here, is the same throughout. I want us to consider one point P1 here and another point P2 here. I want us to have this as the parallel vector B. Of course, this is also having the parallel vector B. Now, if we are considering these two lines, our major interest is to get D. But as you can see, what is this distance D equaling to? This distance D is same as the magnitude of the vector P1 times P2. Okay? Are we still there?
Yes.
So if I need the this one here, if I need the distance, if I need to consider one point on this line, another point on this line, then the distance between P1 to P2 will be what we call the required distance that we need. So how do we get that? So what we shall do is we shall be saying that the distance between the two lines, between the two lines is the length of any line segment, is the length of any line segment, is the length of any line segment, P1, P2. So any line segment, that length there will be the required lengths that we are interested in. So with, of course, P1, that is a point on L1, and P2, that is a point on L2. And this line here is perpendicular. That line there, as you can see, is perpendicular to both lines. If you have this line, it is perpendicular to that, it makes 90 degrees with that. It's perpendicular to both lines. But how do we get the perpendicular distance? This implies that the perpendicular distance D will be same as the magnitude of P1, P2 when we take that one there. But of course, we must know that P1, when we talk about vector P1, P2, this is same as O of P1 of P2 minus O of P1. And also we must recall that vector there, P1, P2, is perpendicular to also vector B, where B is a parallel vector to the lines. Is a parallel vector to the lines. So whenever we have this will enable us to find the value of lambda minus mu or mu minus lambda, which is substituted to find D, which is equal to magnitude of P1, P2. So we are looking at what we call the distance between parallel lines. So if you have a line R1 and R2, so this is line 1, this is line 2. You are interested in this distance. So as you can see, the distance you are interested in is the distance when you are considering the line segment from any point on this line L1 to any point on this line L2. So we are having those points as P1 and P2, P1 on line 1, P2 on line 2. So the distance between these two lines, these 2 points will simply be that length P1, P2, the length of the vector P1, P2. Now to get P1, P2, what we shall do is to make sure that we realize that this vector here, you need to realize that this vector P1 to P2 is perpendicular to this line and is perpendicular to this line. If it is perpendicular to this line, then of course it is perpendicular to B as well. If it is perpendicular to this line, then of course it is perpendicular to B as well. So for that case, that's where we shall get this, that P1 dot P2, that vector P1 P2 dot B will give us 0. And we shall need to use this just to help us obtain the value of lambda minus mu or mu minus lambda, which we shall substitute to find P1, P2. And after finding that, we shall be able to find its magnitude which will help us to find the distance d. So those are some of the procedures that we shall be following when we are obtaining the distance between the parallel lines. And that is where we shall stop, and when we meet, we shall be able to look at how best we can now get the distance between the two parallel lines. But you need to recall this one here, because these are some of the procedures that we shall be following to look at some of the examples.
Okay.
So unless there is a question, that is where we shall stop. Then tomorrow we shall talk about the distance between parallel lines.
Okay.
Yeah, so
Sure.
let us stop there.
Okay. Thank you for teaching.
All right, welcome, please. So nice time. We shall meet, I think, tomorrow.
Yes.
Okay.
Will you send for me? Send for me this
Yeah.
this
Let me
PDF.
send it for you, this PDF.
Mm.
Okay. Make sure you try those numbers. I hope you have
Mm.
put them down. I'm going to forward you this. Make sure you go
Mm.
through it.
Okay.
All right, please.